So you had quiz 3 is come and gone. I haven't seen those scores yet. So we'll have more to say about that later. We got exam 3 next week, I think on Wednesday, right? Yeah. And so that's going to cover all of 20 and then up through 21.3. And what that is mostly definition type stuff, and I'm trying to give you that definition type stuff now. And what I'm trying to do, your book doesn't really teach you much about electrochemistry. It teaches you a few electrochemistry facts, and it teaches you a few calculations, but it doesn't really teach you much about electrochemistry. What I'm trying to do is teach you about electrochemistry. And it all goes back to energy. And I drew the analogy of a waterfall. So I know there aren't waterfalls in Florida, right? And so you don't have this in your head, but you've seen Niagara Falls. Pictures of it. Anybody been to Niagara Falls? Pretty impressive, isn't it? So you got that water coming down over that enormous fall. If you happen to be standing underneath it, your head would be compacted and you would become completely flat. Death would ensue, I'm pretty sure. But, yes, finally, after a lot of agony. But on the other hand, if that waterfall's only 8 feet tall, I can stand under it and the water pours on me and it's wonderful, right? And so what do we learn? The amount of energy available in a waterfall is directly proportional to the height of the waterfall. And this was, I said, when they were designing hydroelectric dams in the 40s, they looked for the biggest dam they could make because that would give you the most dam energy. No, come on. I have told at least 200 jokes. It's great to get a laugh on one of them. That's fine for me. All right. Now, then I drew an analogy with an electrode in a solution. And I said, let's make that tallness of the waterfall, let's make that electron energy. So now electron energy becomes very much like our waterfall. The higher I pump up that electron energy, the greater the energy that electron has. And we said we can do that in an electrolyte solution by attaching a power supply. And we got a little switch there. And we're going to talk about what this reference electrode means, but let's just call it a reference electrode now. And the major thing I wanted to get the point last time was the more excess charge, the more electrons I shove into that metal, the higher the electron energy. So initially the metal is neutral. It has no excess charge, has no excess electrons, no excess positive charge. And those electrons, I'm just going to put that energy right there. So that's, you might call that the zero energy. That's the energy the electrons have when the electrode hasn't been charged. But I said let's think about it this way. I throw that switch for a while, then I open it again. So a little bit of charge leaks in. A little bit. That raises the electron energy. Now I'm going to throw that switch again. I'm going to let a little bit more charge leak in. That raises that electron energy. So basically in this electrochemical experiment, I'm creating waterfalls of different height. So you can't do that with Niagara Falls. But in electrochemistry, I can do that. I can make the energy of the electrons as arbitrarily high as I want by simply connecting it to a power supply, connecting it to the negative end of the power supply, and injecting electrons into it. And as I said, they recruit an equivalent number of cations, and that's where the action takes place in electrochemistry, in that little region, this bizarre little region where it's enriched in cations, and there's an enormous electric field. Yes?
When you say like pump electrons into the electrode, what does that? How do you like pump electrons in?
Simply by attaching it to the power supply. The voltage is like the pump. So the voltage is the pump.
But does it attract electrons from the solution, or where do the electrons come from?
They come from the power supply.
Oh, okay.
So the battery itself is supplying these electrons. That's what the power supply does. So again, the notion is the power supply is injecting the electrons, and that's raising the energy of these electrons. And so now we'll go back to the cloud analogy. By whatever reason, I still don't think people understand that cloud gets excess charge. It gets excess electrons all over its surface. Eventually something happens. Eventually the charge is too great, and it discharges by issuing a lightning bolt. Same analogy here at our electrode. We can get that excess energy so high that ultimately it's got to go somewhere. Where does it go? As I said, now let's do it one more time, electron energy, or this is also a voltage axis. With negative voltages up. How do I make the electron energy higher? I make the voltage you apply to it higher. So I began this as electron energy on Monday, but it could be easily thought of as a voltage axis where the more electrons I put on it, the higher electron energy, the more negative the voltage. So let's say I've got this thing really charged up. The voltage is at this, call it E, at this negative, very negative value now because I shoved a whole bunch of electrons. And here's an empty molecular orbital on a molecule that is randomly walking in that solution. So let's consider two cases. Let's back off a little bit. Back the voltage off a little bit, take off a little bit of that excess charge, and let's say I'm here. Let's call it E1. Well, it's uphill. The electrons have to go uphill in energy to get onto that molecule. I call the molecule ox. But if I'm at this voltage, an electron here will have to somehow get up there in order to jump on, and that's uphill. So I'm a randomly walking ox molecule. There's my electrode. I'm randomly walking. Bop, bop, bop. I bounce into the electrode. I bounce off. Because my empty orbital that an electron might go into is above the electron energy in the metal. So what can I do about that? I can apply a more negative voltage. Burp, 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 burp. I can raise that up now, let's call it E2. And now it's downhill. If I'm an electron there, it's downhill for me to go boom. So now I'm that randomly walking ox molecule. Minding my own business. Boom. I get an electron dumped into my molecular orbital. So now when I randomly walk into the electrode, I emerge as a different molecule. And I just wrote this in a general sense. I was that molecule ox, but I took on some number of electrons, and it could be 1, it could be 2, it could be 3, it could be almost anything. And that converts me into a different molecule, call it red. So, key point here is, just like in the living cell, storing excess charge at an interface stores energy at an interface. In the electrochemical case, I'm going to utilize that energy to make that molecule red. So let's just say I did years ago a a project involving making a new pharmaceutical agent for treating bacterial infections. And one of the steps along the way was electrochemical, and we did that. There was like a 12-step thing to make this molecule, and we did the electrochemical step for them. And so again, it was just this notion that I had to get the voltage of my electrode up high enough such that it was above that empty molecular orbital level. And if I could achieve that, electrons took my molecule ox and made my molecule red. And that was one step in the way toward making that antibiotic that this pharmaceutical company wanted. But that's the essence of electrochemistry there. Now, what I want to do is I now want to translate that into our first electrochemical cell. And this is going to be what we call in electrochemistry an electrolytic cell. Uses energy stored at electrode solution interface to drive a reaction that has a positive delta G reaction. Very important concept. I can take a reaction with a positive delta G such that at room temperature, STP, that reaction is not product favored. And basically, in an electrochemical cell, I'm going to put that energy into the molecule to get that reaction to go, even though it's uphill. So that's what an electrolytic cell does. There's two types of cells. Electrolytic cells use energy. Another way to think about it, electrolytic cell uses electrical energy to make a molecule through this up here, up here. Make a molecule that you want. So again, it could be that pharmaceutical molecule that we worked with so many years ago.
You stubbed it through.
Uses electron energy to make a molecule through a reaction that has a positive delta G reaction. That's the cell I'm going to describe to you right now. But I want to get the definition for the other type of cell, which is a voltaic. That has two names, voltaic, also called galvanic cell, does the opposite. Takes the energy from a chemical reaction with a negative delta G and converts it to a voltage. So what's the classic example of this? A battery. So now you got your two extremes of electrochemical cells. So far we've been talking about an electrolytic cell, where the stored energy at the electrode solution interface is now going to drive a reaction that has a positive delta G. We're going to make a non-spontaneous process spontaneous. How are we going to do that? By putting electrical energy into it. Can't get that energy from nowhere. So we're going to put electrical energy into the molecule. And we're going to drive this process. All right, two types of cells. We're now talking about an electrolytic cell. But the other type is a galvanic cell. We'll return to that here in a minute. Now, so what I want this cell to do, so I want to convince you that I can drive a reaction with a positive delta G. I can drive a reaction that is not product favored. So I'm going to choose a reaction that you know is not product favored at STP. That reaction is two water molecules going to two hydrogen gases plus an O2 gas. So now this reaction at STP, delta G reaction, very positive. And you know this to be true because water molecules don't spontaneously convert themselves into hydrogen and oxygen gas. That would be a real problem for life on Earth if it did. Now, at STP, because obviously remember, entropy wins at high temperatures. This reaction has a positive entropy change. So if you can heat this water molecule up to some really high temperature, that reaction will occur. But at room temperature or anywhere near it, that reaction is very much reactant favored. Do I got that right? Yes. All right. So now, I'm going to do this in an electrochemical cell. How? So here's how I'm going to do it. That's a car battery. That's my power supply. And here's a bucket. Why seawater? Very important. We'll explain why in a minute. But the solution side of the electrochemical cell must have salt of some kind. There must be an electrolyte. There must be. So I'm making it easier on myself. I'm just picking seawater. I want to drive that reaction. I got to have an electrolyte. No problem. There's I've forgotten. 6. I can't remember if it was 6 or 3. 0.6 molar sodium chloride in there. So I've got the electrolyte I need. We're going to talk about why we need an electrolyte here in a second. You just accept it on face value at the moment. Got my car battery. I got my bucket of seawater. I got 2 carbon rods. There's one. There's the other. So these might be, I don't know if you've ever saw and opened a lantern battery, you'll find a carbon rod in there. They're really pretty. They're about, maybe 3/8 of an inch in diameter and about this long. And that's your electrode. And so I got 2 of those. And boom, here's the negative end. I'm going to attach it to that carbon rod. And boom, here's the positive end. And I'm going to attach it to that carbon rod. Okay? So now what's going to happen? Charging, just as I described in this previous example. And this one attached to the negative, we call that the cathode. And a reduction reaction occurs at cathode. And I gave that definition last time. Taking on electrons by a substance is reduction. And at the positive one, an oxidation reaction occurs at the anode. This is called the anode over here. So an electrochemical cell, all electrochemical cells have a cathode in which a reduction reaction occurs, and the other electrode we call the anode, which is where an oxidation reaction occurs. What oxidation and what reduction? I'm going to take this reaction, which has a very positive delta G, and here's what I'm going to do. Boom. Cathode. At some negative voltage. E cathode. Very negative. Up here. Here's an empty orbital on the water molecule. So when I connect that car battery to that carbon electrode, just as we described previously, electrons start injecting into that carbon electrode, raising that voltage more and more and more and more negative, making the waterfall bigger and bigger and bigger and bigger, until finally it's up above that empty orbital level, and bingo, bango, bongo, water gets reduced. What's that reaction? That reaction is I know I'll get this reaction wrong, so let me just make sure I get it right. So that reaction is 2H2O plus 2 electrons gives you an H2 gas. So it's going to be 2H2O liquid plus 2OH minus aqueous. That is a reduction reaction. Reduction reaction occurs at the cathode. Why is it a reduction reaction? A reduction reaction means a chemical substance, in this case water, took on electrons. And just like in my ox to red example, when I was talking a non-general case, I've made a new molecule. I took water, in fact I made 2 new molecules. I made hydrogen gas and 2 hydroxide anions. So at the cathode, a reduction occurs. How does that reduction occur? It occurs because I applied that car battery, the negative terminal of that car battery, to that carbon electrode, and I put so much excess charge on that carbon electrode, raised its negative voltage so high that an electron lowers its energy now by doing that reduction reaction. Now let's go over here to the anode. At the anode, since I'm at the positive pole of the battery, I get excess positive charge. So again, you can think of what the battery's doing. When you apply that battery, electrons leave the battery and go to the cathode, and those electrons come from the anode and go back to the battery. So you got a complete circuit. The negative terminal of the car battery is forcing electrons onto the cathode and sucking electrons out of the anode. So again, I told you this many times in this class. A whole bunch of science can be explained by simple electrostatic arguments. Like charges repel, unlike charges attract. So here we got an example of that. The negative side of the battery pushes electrons into the carbon rod that's the cathode and sucks electrons out. So over here at the anode, sucks electrons out. And it gets the voltage so positive that here is an electron on an occupied, is that how you spell occupied? Not 1P? 1P. Which one? It's a bumper day for me. That's an occupied molecular orbital on H2O. So I've gotten this voltage so low, here it is, call it E anode, that boom, that electron says, I'm happily lowering my energy by simply jumping onto that, by simply leaving this molecule and jumping onto the electrode. So again, I pump electrons into the cathode to make its voltage so negative that electrons jump off into an empty orbital on water, and I suck electrons out of the anode, and I make its voltage so positive that an electron in an occupied molecular orbital can jump off onto the electrode. So at the anode, we've got this reaction. At the anode, we've got this reaction. 2 water molecules, liquid, goes to an O2 gas plus 4H plus 4 electrons. So that is an oxidation reaction. Reduction occurs at the cathode, oxidation occurs at the anode. What does oxidation mean? It simply means the pulling of electrons from a molecule. Oxidation. Loss of electrons from a molecule. So in the net, now another important definition. We got the cathode reaction. We call it the cathode half reaction. So by showing the reaction, so again, our overall reaction that we want to do is, where is it? The overall reaction we want to do is this one with this positive delta G0. We want to take 2H2O liquid, goes to 2H2 gas plus an O2 gas. And what I do in the electrochemical cell conceptually is to split that total reaction into 2 half reactions. So the electrochemical cell takes that total reaction there, gets half of it done at the anode and the other half done at the cathode. It's the simplest way to think about it. It gets half of it done at the anode, the other half of the cathode. So these are sometimes called, this would be the cathode half reaction, and this would be the anode half reaction. Now, key point. If the half reactions are balanced correctly, you add them together, you get the total reaction you want. So again, what the electrochemical cell does is takes the reaction I want and gets half of it done at the anode and half of it done at the cathode to give me an anode half reaction and a cathode half reaction. But when I sum these 2 half reactions up, I should get that reaction back. But you can see I don't quite get that, do I? Because I need to balance. So this brings up the subject. You must balance the half reactions to get the desired cell reaction. We want to do this in our electrochemical cell. If I do it right, I get half of it done at the anode, I get the other half of it done at the cathode. And if I sum up my two reactions, I should get the overall cell reaction. But what do you notice about these two half reactions? This one involves 4 electrons, and this one involves 2 electrons. This is the heart of the notion that you've got to balance the reactions. The same number of electrons going into the cathode has to be exactly the same number as the electrons coming out of the anode. Or put another way, I got to balance this to get that. So what I'm going to do is I'm going to multiply this whole reaction by 2. So multiply that whole reaction by 2. If I do that, I got 4H2O more time. I got 4H2O liquid plus 4 electrons gives you 2 hydrogen gases plus 4 OH minus. So again, now if I add these two half reactions together, I get my desired cell reaction. Because if I add those two half reactions together, the electrons cancel. We'll take it piece by piece. I'm going to add them together. So starting at the top, I'm going to add these two together. Wait a minute, do I got that right? 4 electrons, right? Can't be right. Okay, let me add them together. It's got to be right. 5H2O. So that takes care of that and that. The electrons cancel. Boom. Yeah. What? Here? There's supposed to be a... Oh, sorry. I knew that wasn't right. I just knew that couldn't be right. Right. Sorry.
And isn't there only supposed to be 1 H2O for the...
Hold on. It's in my notes. All right. So, cathode reaction. 2H2O plus 2 electrons goes to hydrogen plus 2H minus. Yeah, you're right. I missed the 2. Anode reaction. 2H2O goes to an O2 plus 4H plus 4 electrons. Took the cathode reaction, multiplied by 2. Why did I multiply by 2? Because now I got 4 electrons on the left and 4 electrons on the right, and they cancel. That was the whole point, to get rid of the electrons. So now I've got how many H2Os? Huh? Because that's the half reaction. That's the half reaction. Where you talking about this one?
Yeah.
Because I multiplied everything by 2. 2 by 2 is 4. 4 waters, 4 electrons, 2 hydrogens, 4 OH minus. I multiplied everything by 2 to get the electrons to cancel. So let's continue. So now I've got 2 and 4, I've got 6 H2O, right? 2 and 4, 6 H2O. Yeah. Did I do that right? Yeah, 6 H2O goes to an O2. That gives you my O2. Plus my 2H2 gas. Plus my 4H plus. Plus my 4OH minus, yeah? But 4H plus and 4H minus, 4H plus 4OH minus gives you 4H2O. So in fact, that's 4H2O. So I got six H2Os, goes to an O2 plus 2H2 plus 4, so plus 4 on the right, on the left, right. That becomes 2. There it is. I took the two half reactions, I balanced them, and I got the reaction that I wanted. Now, implicit on this is I know what the half reactions are. So I knew going into it that this was my cathode half reaction. How do I know that? I know it. I know this is my anode half reaction. I wanted to prove the point that in the electrochemical cell, half the business is done at the anode, the other half is done at the cathode, but if I sum up what's going on at the anode and sum up what's going on with the cathode, I should get back my overall cell reaction. And so it took a little bit of doing and balancing. The first thing I had to do was multiply this one by 2 to get 4 electrons in both cases. That's key, because you can see in the overall reaction there's no electrons. So I got to get the electrons to cancel. But once I did that, I summed them up. I had to recognize that if I got 4H pluses and 4OH minuses, in fact, that becomes 4H2Os. So my reaction was 6 H2Os on the left goes to an O2 plus 2H2 plus 4 H2Os on the right. Or I can now get rid of the excess H2Os. 2H2O liquid goes to O2 gas plus 2H2 gas. So I drove a reaction in this electrochemical cell that is, from a thermodynamic point of view, uphill. I took reactants low in energy, the water molecule, and I used the energy from the battery to split that water molecule. Part of the splitting was done at the anode, part of the splitting was done at the cathode, but if I know those two half reactions, and I balance those two half reactions, boom, I get my total cell reaction back. And again, this is the heart of what we call an electrolytic cell. An electrolytic cell takes energy, in this case from a car battery, shoves it into these two electrodes, and that cell then drives this reaction that has a very positive delta G. That reaction is uphill. Take water low in energy, make hydrogen and oxygen gas high in energy. Where did the energy come from? Came from the battery. So an electrolytic cell takes electrical energy and uses it to drive a reaction. A reaction, as in this case, that's thermodynamically uphill. That's what an electrolytic cell does. So we got anodes, we got cathodes, we got electrolytic cells, voltaic cells. Okay, very good. Now, right. Now where do I want to go? Okay, good. All right, now let's switch gears to our second type of cell, a galvanic or voltaic cell. So that was your introduction to electrolytic cells. Let's switch gears now and talk about a voltaic This is the opposite type of cell. The cell reaction has a negative delta G reaction. So in the electrolytic cell, the cell reaction had a positive delta G. It was thermodynamically uphill. The voltaic cell begins with the opposite. The cell reaction has a negative delta G, and that delta G reaction gets converted in the electrochemical cell to a cell voltage, which is a battery. So now we can complete the loop. I said that in this device up here I used a car battery to provide the energy. That car battery provides the energy because on board that car battery is a set of chemical reactions that have a negative delta G. Thermodynamically downhill, that car battery takes reactants way up here in energy and converts them to products way down here in energy and converts them to a voltage. So the simplest way to think about a voltaic or galvanic cell is that it's a battery. And indeed, so you can see we've completed the loop. We use one type of electrochemical, in this example, we use one type of electrochemical cell, a voltaic cell, to drive the second type of electrochemical cell, an electrolytic cell. So in this example, we've got a voltaic cell and an electrolytic cell. The voltaic cell provides energy. The electrolytic cell consumes energy. Again, very important. The voltaic cell provides energy because inside that voltaic cell is a chemical reaction with a negative delta G. So the voltaic cell provides energy in the form of a voltage, and the electrolytic cell uses that energy to do a chemical reaction we want to do. In this example, split water. So those are our two cells. Now, let's take an example of a voltaic cell. We'll take a beaker here, and I'm going to take zinc. And as it turns out, it's going to be the anode. So it's a zinc rod, a zinc wire, piece of zinc foil, some form of zinc wire. And I'm going to put it in 1 molar zinc sulfate, aqueous. So again, important, the solutions in electrochemical cells must contain ions, must contain a salt, must contain an electrolyte. In this case, it's 1 molar zinc sulfate. And then I'm going to take 1 molar copper sulfate and put a copper wire. Now, in this case, I'm going to connect them by a voltmeter. Now there's one critical part of the cell that I have not put in here yet, and nothing's going to happen till I do, but what I want to explain to you before we add that last piece of the equipment is this cell. Again, if we take electron energy, just as we did before, the energy, there's the E of the anode way up there. Again, this is, or we say negative voltages up. Up. So the anode is at this very negative voltage. And there's electrons in the anode, the zinc. And as it turns out, way down here in the solution, this is now the cathode. This is an empty orbital. On copper 2 plus in the solution, and in the net, the electrons are going to leave the anode and go in. They're not going to go that way, they're going to go through the circuit, but I'll stop here by simply saying that in this case, the anode half reaction is going to be zinc solid. Goes to zinc 2 plus aqueous plus 2 electrons. And the cathode half reaction is going to be copper 2 plus aqueous plus 2 electrons. Goes to copper. Overall cell reaction, just add them up. Now we don't have to, now the electrons are balanced. You take a zinc solid plus a copper 2 plus, and you make a copper solid plus a zinc 2 plus, and you get about 1 volt from this. So this is a battery that produces 1 volt. And it's because the electrons in zinc are way up here in energy, and that empty orbital on the copper 2 plus is way down here in energy. So we got a negative, so we start with reactants up here in energy, we make products down here in energy. We'll pick this up, oh, I guess we don't have class Friday, we'll pick this up Monday.